Hello, welcome to this new video of Math-S400, Mathematics and Economic Modeling. In this lecture, we're going to see an important theorem that's called the extreme value theorem. And short, it says that any continuous function on a compact domain reaches a maximum, an extreme value, that is, and also a minimum. So let's get started. So consider a function f that might start on some domain, right? So here, in general, D is a subset of k-dimensional Euclidean space, and it takes vectors and produces real numbers. And you would like to find a value in the domain. Okay, so we're maximizing over all x in the, let's say, the domain of f of x. Okay, so let's assume that D is a subset of R, and you can make a picture. So here you have domain and you have a function, and in this case, for example, here this value, this x here, and this is f of x. X is an extreme value in the sense that f of x is highest among all possible values of the function. Okay, so in general, not every function can be solved, right? This problem cannot always be solved for any function or on any domain. So let's give two examples. For example, let's be f to be a function, let's say from the interval 0, 1, excluding 1, to R. And let me draw this function. So here we have 0, here we have 1, and for example, let f of x be equal to x. Okay, so this is the 45-degree line, but the domain does not exclude 1. So here we don't have a value at point 1. Okay, so we see that if you want to maximize f, what value of in the domain is going to give you the maximum value of f? Well, it's going to be the value that's arbitrarily close to 1, but you cannot pick 1 because 1 is not in the domain. Okay. Max x in 0, 1 of f of x. Okay, so this problem is not well defined. There's no maximum for this problem. Okay, so consider other problem. Okay, again, let's now, in this case, for example, let f go from 0, 1 to R. Okay, so now it's a closed interval, and let, for example, f x is equal to x for x smaller than 1/2. Okay, and let f of x equal to 0 for x greater or equal to 1/2. Okay, so here we have the value 1/2. If x is smaller than 1/2, then f of x is equal to x, so we have the 45-degree line, and for x greater or equal to 1/2, we have this. Okay, and now the value 1/2, at 1/2, f of x is equal to 0. So we have this function here. So again, if you would like to maximize the function f of x over the domain 0, 1, we see that the maximum is arbitrarily close here below 1/2, but it never reaches this point here. So again, the maximum is not well defined. Okay, so there are several cases where this problem does not have a solution. Okay, so here we have seen an example where the problem was because the point that we would like to include was not in the domain, right? So here the set was, we can say, not closed. Okay, here in this case we had a problem that the function made a jump at 1/2, and in a certain sense we will see that these are the only two cases where things can go wrong, right? So for example, here we had the problem that as you will see, the domain is not compact, right? So it's not closed and bounded. Here we have the problem that the function that we would like to maximize is not a continuous function. Okay, so we will see that if the domain is compact and if the function is continuous, then we are indeed possible to maximize the function, or find the value in the domain that maximizes the function over the domain. So in order to get to the extreme value theorem, we will first demonstrate another theorem. That's the following. So if D, which is a subset of Rk, is compact, okay, so you know what compact means. It means that D is closed and it's bounded. Okay, then f of D, okay, so this is the range of the function f under the domain D, is also compact. Okay, so here we call f of D is the values, all the values in R, such that there exists a vector x in D, such that f of x is equal to y. Okay, so these are all the values that the function can take over the domain D. And observe that this is a subset of R. Okay, so f goes from Rk to R. This theorem says that if the domain is compact, then this range of values is also going to be compact. Okay. So what we need to show is that the domain is compact. Oh, and I forgot something important. And f is continuous. Okay, so the domain is compact and f is continuous, and the range of f will also be a compact set. Okay, so the continuity thing is very important. Okay, so let's assume that D is compact and f is continuous. We have to show that f of D is also compact, so this means that we need to show that this set here is also closed and bounded. Okay, so in particular, if you take a sequence of elements in the set that converges to some limiting number, then the limiting number should also be in the set, and that means that it's closed. And second, there should exist a number that's such that the absolute value of any element in the set is lower or equal to this number. Okay, so we need to show that this is closed. And so we're going to work in two steps. In the first step, we will show that f of D is bounded, and then second step, we will show that f of D is closed. So point 1. So you're first going to show that f of D is bounded. Okay, so and the proof is going to work by contradiction. Okay, so the contradiction, we're going to assume f of D is not bounded. Okay, so first of all, remember what it means for a function to be bounded. It means that there exists a number m, which is that for all a, y, and f of D. Okay, so for every number in the domain, the absolute value of y is lower or equal to this number m. Okay, so if you assume that f is not bounded, then you have that for all m, for all numbers, these can be integers, there exists something in the range of f such that the absolute value of y is greater or equal to m. Okay, so this holds for all numbers. So in particular, it holds for the number 1, it holds for the number 2, it holds for the number 3, and so on and so on. Okay, so we can set m equal to 1. Well, then we know that there's a y1 in f of D such that y1 absolute value is greater or equal to 1. M is equal to 2, then there exists a y2 in f of D such that y2 is greater or equal to 2, and so on and so on. Okay, so in general, if m is equal to n, then there exists a yn in the range of f such that yn is greater or equal to this n. So if we continue doing this, plugging in more and bigger values for m here, then in the end what we will get is we'll get a sequence of numbers in the range, okay, such that for all n, yn is greater or equal to n. Okay, so here we have y1, y2 to yn, and so on and so on. So this is my sequence of y's. Okay, so this is in the domain, and because y1 is in the domain, we know that there exists an element or a vector, and so if y1 is in the range, then we know that there exists an element in the domain such that f of this element is equal to y1. Okay, so for example, there exists for y1 there exists an x1 in the domain such that f of x1 is equal to y1. Okay, so in the domain we can associate a number x1, and then y1 is equal to f of the vector x1. Okay, y2 we can find vector x2 such that y2 is equal to f of x2, and so on. Generally we have an xn such that yn is equal to f of xn. Okay, so this follows from the fact that all the y's are in the range of f. Okay, so this gives you a sequence of x's in the domain, okay, which corresponding value under the function f is equal to this y1, and so on and so on. Okay, so now we have a sequence xn in the domain. Okay, so what do we know about this sequence? Well, in general, it's just a sequence of vectors. However, we know that the domain is a compact set. Okay, so we can use the Bolzano-Weierstrass theorem to say that there exists a convergent subsequence. Okay, so there exists a sequence x phi n d. Okay, so there exists a subsequence in D such that x phi n converges to some vector, let's call this x. Okay, what do we know? The domain is compact, so it's also closed. So this x, any sequence with a limit in a closed set, the limit, any sequence in a closed set which has a limit, then the limit should also be in a closed set, so x is in D. And in particular, we can look at the function value under x of this thing in the domain. So this is simply a number in R. Okay. So before I continue, what we also have, y was great. So in general, y1 was greater or equal to 1, y2 was greater or equal to 2, yn was greater or equal to n, and so on. Okay, so f of x2 is greater or equal to 2, f of xn is greater or equal to n, this is greater or equal to 1. Okay, so in general, f of x phi n will be greater or equal to phi n. Okay, this follows from the definition of the y's that we have shown, which we have seen here. Okay, so what do we do now? This gives us a value, number in R. Okay, so take n greater or equal to, so this is a value, right? So take n greater or equal to f of x, and in particular take n, let's call this big N. So we take a value big N that's greater or equal to fx. Okay, so remember that we had the sequence x phi n, which was a subsequence of xn. So we can look at the subsequence of the sequence where we only look at the phi n's that are greater or equal to this n. Okay, so this generates the sequence x phi n, and then only for phi n's greater or equal to this n. Okay, so what do we have? We had this subsequence of x's here. You restrict the subsequence to only the sub indices that are bigger than this number, which is bigger than f of x. Okay, and this, so basically we cut off an initial portion of this sequence here, and what we get is another subsequence which is now a little bit smaller because we cut off some part at the beginning. Now I hope you realize by only cutting off a part at the beginning, we don't interfere with the convergence of the sequence, right? The sequence still converges to the vector x. Okay, so this sequence still converges to x. However, for all phi n's in the sequence, we also have that f of x phi n was greater or equal to phi n, right? This was just by we call here, this is this inequality, and this obtained from the inequalities or the definitions of the y's that you had here. So x of phi n is bigger than phi n, and we only looked at phi n's that are bigger than n. Okay, and this big N is greater or equal to f of x. So what can we do now? Now we can take the sequence or the limit for n going to infinity here, and then by continuity of f, this sequence goes to x, so f of the sequence goes to f of x. Okay, so this is a sequence of numbers, and each number is greater than big N. So in the limit, this has to be greater or equal to this big N. Okay, so if you have a sequence of numbers, and every number is greater or equal to some fixed number, here n, then the limit also has to be greater or equal to this fixed number. And, sorry, this has to be strict inequality, and we chose n to be bigger than f of x, so this gives you that this is greater than f of x. So in the end, what you get is that f of x is strictly bigger than f of x, and this gives you the contradiction. Okay, so let's recapitulate, right? So if this range would not be bounded, basically what we can do is we can take a sequence of values in the range which get bigger and bigger and bigger and bigger. Okay, this sequence of values in the range generates a sequence in the domain, and from the sequence in the domain, because the domain is compact, we can get a convergent subsequence. Okay, but along the subsequence, the function values also get bigger and bigger, right? Because these associated values were bigger and bigger. So in the end, what does this give you? This gives you a subsequence whose values in the limit is going to get bigger than this value f of x that we have as a real number, because f is defined in the entire domain. Okay, so this generates the contradiction. Okay, so far we have seen that the first part here is that the range is a bounded set. Okay, second thing we need to show is that f of d is a closed set. And how do we show that the set is closed? Well, we take a sequence in the set, right? So let yn be a sequence in f of d, and yn converges to some number y. Then we need to show that y is in f of d. Okay, so that's what we need to show. Okay, so here we have a sequence yn converging to y. So let's write down the sequence. So the first element is y1, then you have y2, then you have y3. So in general we have yn, and so on. So in the limit this converges to y. So all of these elements are in the range. Okay, so this means if y1 is in the range of f under the domain D, that there exists a vector in D, let's say x1, such that y1 is equal to f of x1. Okay, here there exists a vector x2 such that y2 is equal to f of x2. There exists a vector x3 such that y3 is equal to f of x3, and so on and so on. So in general there exists a xn such that yn is equal to f of xn. Okay, so this gives a sequence xn in the domain D. What do we know about this sequence? Well, nothing much. It can go either way. However, the domain D, and again here we use compactness, so D is compact, which means that this sequence has a convergent subsequence. So again, here we use the Bolzano-Weierstrass. So there exists a convergent subsequence x phi n such that x phi n converges to some vector, call it x, and because D is compact, so it's also closed, we have that this is also in the domain. So this limiting element is in the domain. So if it's in the domain, well then we know it has a function value which we call f of x. Okay, and f of x is in the range. So what's the idea? Well, the idea is the following. You know that x of phi n converges to f of x, and because f is continuous, this means that f of x phi n converges to f of x. Okay. The idea is now to show that this y here, which we have to show that it's in the domain, we will show that this y is equal to this fx. Okay, so how can we see that this is indeed the case? Well, remember that f of x1 is equal to y1, f of x2 is equal to y2, f of x3 is equal to y3, and so on. So in general, f of xn is equal to yn. So here f of x phi n will be equal to y phi n. Okay, so y phi n is a subsequence of yn. Okay, so here we had a sequence of x's. We restricted the sequence to a subsequence. This here, this phi n's, looks at the corresponding y's that are associated with this subsequence of x's. Okay, and if you do this, we get a subsequence of these sequence of y's. And of course, because the sequence of y's converges to y, any subsequence of a sequence that converges to the same limiting number. Okay, so here we have a sequence of y's that converges to y. Here we have a subsequence that converges also to the y, but this here says that this subsequence converges to f of x. And of course the sequence can only converge to one thing, so we see that f of x is equal to y. And if f of x is equal to y, well, x is in the domain, so y has to be in the range. And this demonstrates the proof. Okay, so if f is continuous and the domain is compact, then the range will also be compact. So now we're ready to state the extreme. And the extreme value theorem is the following. So the subset of Rk is compact. We have f, which is a function from D to R, is continuous. Well, in this case we have that maximum of f x and D exists. right? And not only the maximum, but also the minimum of x in D also exists. Okay, and we already did the heavy lifting of this theorem, so let me quickly give you the proof. So here you look at the maximum of f of x, where x goes over all the elements in the domain. So this is nothing else than looking for the maximum element in the range of f. Okay, because if x goes over D, then f of x goes over the range of f. So basically we're looking at the maximum element of this set here. We're looking at the maximum element of the range. So how can we do this? Well, we know that if D is compact, well, from the previous theorem, then you know that f of D is also compact. Okay, and f of D is a subset of R. Okay, and we previously, I think 2 or 3 lectures ago, we have seen that any subset S, subset of R, and S compact, then the supremum of S is also an element in S. Okay, so here f of D, the range of f, can take the place of this set here, right? Because it's a subset of R and it's compact by the fact that we have shown previously that if the range of a continuous function under a compact domain is compact. So in particular, this shows that the supremum of the range is also in the range. Okay, and the supremum of the range is greater or equal to anything in the range, right? Because the supremum is an upper bound on the set. So if the supremum is an upper bound and it's greater or equal to anything in the set, well then the supremum of f of D should be equal to the maximum of f of D. Okay, so how can you find the maximum? Well, you look at you find the supremum of an f of D, right? If this is equal to y, well then find the x in D such that f of x is equal to y. And you know that such an x exists because y is in the range of f. And you can do a similar thing for the minimum. You just change the supremum by the infimum. So this shows the extreme value theorem, which is a very valuable theorem. Basically, any continuous function on a compact domain reaches a maximum and a minimum on the domain. So we're going to see a quick application of the extreme value theorem, and for this we're going to look at the standard consumer maximization model. Okay, so we're looking, what's the standard consumer maximization model? Well, we have a consumer that consumes bundles. Okay, so here X is a bundle of goods in Rn. Okay, so here X is a vector. Actually, they're in Rn plus, right? So you cannot consume negative amounts. So here X1 is the amount of good 1 that you consume. X2 is the amount of good 2 that you consume until the amount of good k. Okay, it's not Rn but Rk. And what is a consumer doing? Well, he's maximizing the utility of consuming the bundle X, subject to the fact that X is in the budget constraint. And how can we define the budget constraint? So normally we do this by defining a price vector, okay, which is in Rk++, right? So it's strictly positive prices. Okay, so if I look at the price vector P, this is the price of good 1, the price of good 2, the price of good 3, until the price of good k. Okay, and all these are strictly positive, right? All prices are strictly positive. And then the consumer also has a budget, which is just simply a number, and we take this number to be greater or equal to 0. So the consumer has a total amount of money equal to M, and then it buys goods the amount x1 at price p1, the amount x2 at price p2, amount x3 at price p3, and so on. Okay, so the total expenditure is the sum from 1 to k of pi xi. Okay, and you know how we can write this. This is nothing else than the dot product between the vector p and the vector x. So this has to be less or equal to the expenditure. Okay, so what does the consumer do? Maximizes the utility function. Okay, so it chooses x such that p of x is smaller or equal to m, and then of course x is greater or equal to 0, right? X is in RK plus. So all the vectors that satisfy this is called the budget of the consumer. Okay, so in two-dimensional space, this is consumption of good 1, and this is the consumption of good 2. Then normally this is m over p1. Here we have m over p2. So this is maximum amount of good 1 that you can buy, maximum amount of good 2 that you can buy, and then you have the budget constraint here. So all the vectors x that satisfy these two conditions are in this shaded region over here. Okay, so this is called the budget constraint of the consumer, and we call this the set B. So this is the set of all vectors x. So let me rewrite it at the bottom where I have a bit more room. All right, so we call this the set B is the set of all vectors x in Rk such that x is greater or equal to 0 and p times x is lower or equal to the budget. Okay, so basically what the consumer is doing, well, he's maximizing the utility of x given that x is in the set. Okay, so if you rewrite it, we have that we maximize u of x given that x is in B, or we maximize the number in the range of u b. Okay, so this is a very shorthand notation for this long maximization problem. Okay, so when do we know that this problem has a solution? Well, we can use the extreme value theorem. So first of all, we need to require that the function that we're maximizing is continuous. So u goes from Rk plus to R. It's continuous. So basically this says that if you have a sequence of bundles that converges to some bundle, then the sequence of utility values that you get at these bundles will converge to the utility at the limiting bundle. Okay, so this is continuity of the utility function. And then the second condition is that this set B here, B is a compact set. Okay, so in particular it should be closed and it should be bounded. Okay, so let's show these two properties for the budget set. Okay, so at least we know that if you have a continuous utility function, then the utility maximization problem is well defined. So first of all, in order to show that this set is closed, what do we need? We need a sequence of bundles, okay, in the budget set, and the sequence xn converges to some bundle x. And in order to show that the set is closed, we need to show that the limiting bundle here is also in B. So what does it mean for this sequence to be in B? Well, this is equivalent to saying, just look at the definition of B, right? This is saying every bundle in the sequence should be greater or equal to 0. And if we multiply p times xn, then this should be lower or equal to the income. Okay. And this sequence of bundles converges to x. So what do we have here? Here we have a sequence of vectors. Every component is greater or equal to 0, and the sequence of bundles converges to this bundle x. So in general, this implies that, okay, so let me write it this way, xn is greater or equal to 0. this sequence of vectors converges to x, and every vector in this sequence is greater or equal to 0. So by taking limits, we know that x will also be greater or equal to 0. This is preservation of inequalities when taking the limit. Okay. Then here, one way you can see that this will hold for the limiting bundle x is the following. So we have the sum of I1 up to k of pi xi ni, right? This is the ith item in vector xn. And you can see, I hope you see that this is a continuous function of the x. Okay, so if this is a continuous function of the x and the x's converge to the vector x, then this will converge to I1 to k of pi xi, where x is here in the limit. So this is equal to p times x. Okay, so in general, p times xn is lower or equal to m. And this here, this sequence of numbers, right, these are numbers, converge to this number here, p times x. And then again, by the preservation of continuity, we know that this is less or equal to m. Okay, so this argument shows that the limiting bundle is greater or equal to 0, and the price times the limiting bundle is less or equal to m. So if you look at the definition of the budget set, from these two things, it follows that limiting bundle is in B, so B is a closed set. So final thing that we need to show is that this budget set B is bounded. Okay, so what's the definition of bounded? Well, we have to find a number, let's call it m, such that for all bundles in the budget set, the norm of the bundle, okay, is lower or equal to m. Okay, so in particular, if this is good 1, if this is good 2, budget set, then you have to be able to draw a ball of some radius around 0, which is here, such that the entire, this is a ball, right? It's a crazy ball. The entire budget set is in this sphere or this ball of some radius m. Okay, so one thing that we already see immediately from the picture is that there's some maximum that the amount of the goods can take, right? So this normally will be m over p1, and this will be the income over p2. Okay, and you always have that the good of some good, the amount of some good will always be lower than m over the price of the particular good. So in order to see this, let's x be in the budget set. So this means that for all goods xi is greater or equal to 0, right? And if you sum I from 1 to k of pi xi, this is less or equal to your income. Okay, all the x's are greater or equal to 0. So if you set all the x's equal to 0 except for 1, let's say good j, then we get that this is greater or equal to pj xj. Okay, so this inequality holds because all the x's are greater or equal to 0. And then if you look at good j alone, then we have that xj, put the price to the other side, is less or equal to m over pj. Okay, so this is how you get to this maximum here. So these numbers, m over the price of the particular goods, will be quite interesting, right? So we have the m over price of good 1, m over the price of good 2, m over the price of good 3, and so on until m over the price of good k. Okay, and prices are strictly positive, so all these numbers are finite. So let's try to bound this norm here. Okay, so we have the norm of good x. If you look at the definition, this is the square root of the sum from 1 to k of xi squared, and all the xi's are less than m over pi. Okay, and the x's are non-negative, so we know that this is less or equal to the square root of I1 to k of m over pi squared. Okay, and now we basically got rid of all the x's. Okay, so this is in principle this is just a number, right? It only depends on income and prices. But you can simplify it a little bit further, right? So let's, for example, set n to be equal to the maximum of all these numbers. Then you know that this is smaller or equal to the square root of 1 to k of n squared, right? Because m over p1 is lower or equal to n, m over p2 is lower or equal to n, and so on. They're all non-negative, right? So this is less or equal to this. And if you calculate this, we can put n outside of the summation and the square root, and then you multiply by square root of k. Okay, so you want to find a number m such that for all xn the budget norm of x is smaller or equal to m. What we can do is we can define m to be equal to square root of k times n, where we define n to be equal to the maximum of the income over the prices. And then this is a proof that indeed the norm is less or equal to this number here. Okay, so this shows that the budget set is bounded and that it's closed, so the budget set is compact. So if you maximize, if you have a consumer with a continuous utility function subject to a budget constraint, then this consumer will always be able to find the best bundle, the bundle that maximizes her utility function.